This is part 2 of the chapter 2 lecture note. Here we go. Okay, I think we left off here. We were still talking about isotopes, and let me make sure the pen is on. Okay, there and on this page there are 3 examples of hydrogen isotopes. One is called protium, and it contains a proton and an electron, 0 neutrons. The other isotope is called deuterium, and it contains a proton and a neutron in the nucleus and 1 electron. And then tritium contains 1 proton, 1 electron, and then 2 neutrons. So they're all hydrogen atoms because they all contain 1 proton each. That 1 proton is what defines the atom to be hydrogen. But they're isotopes because they contain different numbers of neutrons. Now, again, when we get to a slide that has a video clip on it, I'm just going to refer you to, I don't think the recorded lecture is really the place for watching a video that's already recorded. So I'm not going to waste time, watching that. But you can go to the slides, to the chapter 2 slides, and this is, I will give you the slide number. This is slide 11. So we're going to move on to slide 12. But you can go to slide 11 if you would like, and just kind of jot that down if you want to, and go to slide 11 and watch the video clip on isotopes. You can see in this picture that these are archaeologists, which are uncovering bones of a mammoth, a pygmy mammoth. I've heard of a woolly mammoth. This one is called a pygmy mammoth. In fact, now that I look at it, there's 4 archaeologists in this picture, but I just noticed the 2 at the top. But anyway, they're very carefully uncovering the fossilized bones of a pygmy mammoth. And the reason this example is being used is because the way that biologists are able to determine the date or the age of a fossil is by using radioisotopes. Some isotopes emit radiation, and they emit radiation in the form of neutrons, protons, and electrons. And radiometric dating takes advantage of this, uses the fact that isotopes decay over time. They emit radiation, or they emit subatomic particles over time. One example is carbon-14 over time will decay to nitrogen-14. So a researcher can take a sample of a fossil, like a bone or any kind of fossil, and compare the ratio of carbon-14 in the atmosphere to carbon-14 in the fossil, and determine the fossil's age. Now, carbon dating can be used as long as the fossil is less than 50,000 years old. But for older fossils, scientists will use uranium, which decays to lead, and then potassium and rubidium are other isotopes that are used. So isotopes are used in radiometric dating because we know a property of them called their half-life. Anyway, we use that in a mathematical formula to determine the age of the fossil. And this, of course, is the periodic table of the elements. Every symbol on here is a symbol of one of the elements, and we can take one that I'm trying to find one I can read. The oxygen, I can't, hold on. There we go. It's still blurry. Okay. Well, sodium I can read. Sodium I can read pretty well. It's right here. Okay. So sodium's atomic number is 11 and its atomic mass is 22.9 something. So with the atomic number being 11, we know that sodium has 11 protons and 11 electrons because the number of electrons and protons is equal in a neutral atom. Now the number of electrons can change if the atom has a charge, but we're assuming that these atoms currently don't have a charge. And then you take the atomic mass and you round it. So 22.9 rounds to 23, and you subtract 23, take away 11, and that gives you 12 neutrons. So that's just one more example. There are many, many more of how you can use the periodic table to determine the number of protons, neutrons, and electrons in an atom. If an atom has a neutral charge, then the number of protons equals the number of electrons. Because the protons have a positive charge and the electrons have a negative charge. So if for hydrogen, for example, if you have one proton, you have one positive charge. And if you have one electron, you have one negative charge. And as you know, both of those will cancel each other out, which will leave you with a zero charge. Electrons in atoms will reside within energy levels or electron shells. And electrons tend to fill up the lowest energy levels first, or the ones that are closest to the nucleus. So hydrogen, for example, only has one electron, so that electron fills the first energy level or the first orbital, or it resides in the first orbital closest to the nucleus. Now, the concept of valence shells, the valence shell is the outermost energy level or the outermost electron shell that contains electrons in it. So the valence shell for hydrogen would be the 1n or the first energy level. And the valence shell for lithium has 2 electrons in its first energy level, and it's got 1 electron in its second energy level. So the valence shell would be the second energy level. And the valence shell for sodium is the third energy level, and so on and so forth. So these are showing you that whatever period 1, period 2, period 3, whatever period that the atom is in will tell you its valence shell. So if it's in period 1 or row 1 on the periodic table, like hydrogen and helium, then it will have electrons in the first valence shell only. And if it's in period 2, it will have electrons in the second valence shell only. The groups also give you information. Group 1 are all, in this whole entire column, group 1 are all atoms that contain 1 electron in their valence shell. And group 14 contain 4 electrons in their valence shell. Group 17 contains 7, and group 18 contain 8 electrons in their valence shell, all except for the atoms in period 1, which don't have enough electrons to fill up their second valence shell. And the first energy level, or the first electron shell, is filled with 2. The second, third, fourth, and so on are filled with 8 electrons. So 2 electrons will fill up the first electron shell, the first energy level, and then 8 electrons will fill up the second, third, fourth, fifth, sixth, seventh, and so on. And that is called the octet rule. The first 2 outer shells It says when the first two outer shells are filled, each will have 8 electrons. That's the octet rule. And that is all except for the very, very first energy level, which is filled with 2. Okay, so we also need to talk about, there's not a lot of notes on this, so I'll just have to explain it. We also need to talk about stability. So the octet rule helps us to understand what makes an atom stable is having a filled or complete valence shell. So if you look at group 1, the atoms in group 1 are unstable because hydrogen would be stable if it had 2, because 2 electrons would fill its outer energy level or its first energy level. Helium is stable because its first energy level is filled. It has 2 electrons. It's filled with 2 electrons. But hydrogen is unstable because it only has 1 electron. So in group 1, all of the elements in group 1 have 1 valence electron, or 1 electron in their outer energy level. Lithium, for example, has 1 electron in its second energy level. Its first energy level is filled with 2, but its second energy level only has 1. And remember, the second energy level all the way to the very last energy level will be filled with 8 electrons. So lithium could potentially hold 7 more electrons in its second energy level. Sodium also has just this 1 valence electron. So all of the atoms in group 1 have 1 valence electron. All the atoms in group 14 have 4 valence electrons. The atoms in group 17 have 7. Here's 2, 4, 6, 7. And then if they're in group 18, they're either filled with 2, like helium, or all the rest of them have 8 valence electrons. And that means they are stable. So group 18 are called the noble gases. And they are stable because their valence shells are filled. Excuse me. So what would it take to make group 1 stable? If group 1 atoms were to lose their valence electrons, then lithium would have its first energy level filled already if it lost that 1 valence electron. Sodium would have 8 electrons in its outer energy level if it were to lose that 1 valence electron. But if you come over here to group 17, fluorine and chlorine would be stable if they were to gain 1 valence electron. Okay, so if fluorine or chlorine gained 1, they would each have 8. Group 14 could gain 4, and the atoms in group 14 would be stable. Okay, on this slide just explains that Bohr models, which are like these models of atoms, are called Bohr models. That's when you have the protons and the neutrons in the center and the electrons fill in orbitals, the first energy level, the second energy level, and so on. But, excuse me, the reason that the Bohr models are not complete is that electrons really don't orbit. And we use this word orbital, and it's very misleading because electrons move around very fast and they move in a random motion. They do not orbit like a planet orbits the sun. The best way that I know how to explain this to you is to move on to this slide where you can have a picture. But the first subshell, or the first energy level, electrons it's a spherical shape. So here's your nucleus. And what would happen is that at any given time, you would be likely to find